I have already posted as an announcement. I have posted the answer of this example that I have solved in the previous lecture as a PDF file, okay, for your reference in the Teams. Today, inshallah, my objective to give you uh, introduce how do we now choose a city such that one saturate if we have a DC content in the fault current and also if there is a remnant flux in the core, okay, the core and we'll call this CT dimensioning. It means how do you uh, reduce the size of the CT such that it won't saturate for DC and remnant flux. And then I will finalize with how that affects how CT saturation affect the protection systems in general. And then I will cover the second part, which is the voltage transformers. So as a summary in the previous like lectures on this topic, I've shown you have two factors that can lead to CT saturations at steady state. First of all, the magnitude of the secondary current, right? And the second one, because we know VK, we have to find VK or V class. VK, which is the voltage class, has to be greater than I secondary times R of the CT plus R burden. So this IS is I primary over the CT ratio. I will say CTR or the ratio. And as we can see, the CT ratio, now the Z burden, which is this is the burden, okay, of the connection wires and the load, the relays and so forth, and also the magnitude of the current, which also depends on the ratio that you have selected for the CT. Now, from the steady state point of view, why do we want to limit this voltage? Because this voltage is proportional to the knee point voltage and of the pH characteristic, which is this is Vs versus the IE, and that's Vk or V naught, at which we don't want the reach 10% error. Okay. So what is this Vs or Vk? This is the voltage class. This is the V at the secondary. The voltage at the secondary. This is the voltage at the secondary. What you know from machine school. Have you before got this? Do you know this equation from machine school course?
دكتور الصوت يقطع.
I'll try to change the network. 1 minute. connections, stable connections, but I don't know what's going on nowadays. Okay. Have you heard about this equation before? Or know about this? That the voltage at the secondary of induced voltage of a transformer equal to this. So V is equal to V induced voltage is equal N to N phi by dt, right? According to Faraday's law, the flux linkage rate with respect to in a transformer. So the CT is also same thing. So the voltage induced at the secondary side is proportional to this. Now phi is equal to phi maximum sine omega t. Then if you take the derivative of that, okay, I will be able to find that Vs, this Vs is equal to, this is an instantaneous value now, so equal to n phi m phi m, and this cosine omega t times omega, so times omega cosine omega t. Okay, and this one is equal to take the RMS of the, this is V of t. So what is V RMS? Vs. I'll take this as over root 2. So it's by 2 pi f, which is omega, times n, times phi maximum over root 2. That's the RMS value of this. And this is phi m is equal to P times the flux density. Okay, so this, and 2 pi over root 2 is 4.44 times n times phi f n phi, so P times the area, P maximum times area of the CT in this case. So this represents the voltage RMS value, and this is the peak value of the voltage. As you can see, now if we increase the cross-sectional area of the core, I can go to higher voltage, right? Secondary before CT saturate. And V maximum represent now the maximum flux density that this I should not exceed in order to not to exceed the saturation point. Okay. So this is now a frequency. Of course, we will fix our frequency to 50 hertz to say n number of turns, which is we know. So now deterministic factor in the flux knee point is the maximum flux that you should not. If you have pH curve also, you will have same pH characteristics, which is okay, and that's represent our knee point, the P maximum, which gives you the voltage maximum that we should not exceed, which is Vs, okay, which is Vk, and that Vk we should select such that it should be greater, this voltage NIBO should be greater than the secondary developed voltage at the secondary side of the CT. Okay, this is from the steady state point of view. Now, if we have a CT that is from the transient point of view, we want to consider now the Now from the steady state to avoid CT saturation, I have to choose a CT class. First of all, I can reduce the effect of saturation by bringing this quantity lower than the knee points by increasing the CT ratio, by reducing the burden, okay? By probably for the design, I have to increase this cross-sectional area of the core. It's my choice from the beginning, okay? So I can reduce burden ratio and choose at the end a proper class, CT accuracy class. So the criteria in steady state mostly is we are looking for the product of IS times ZB, or this is the relationship. And if you can see the at steady state also, this figure shows the secondary current versus the primary current of the CT. Refer to the okay. Now, if you take the ratio of the secondary current over the or the primary current over the secondary current, you get a constant value, which is the ratio of the CT. For ideal CT, this ratio has to be same, regardless of the primary current with respect to the secondary current. Now, for an non-ideal CT will, as you go to the knee point, CT ratio will get reduced, okay? And because current and secondary will decrease by IE, which is the magnetizing current. And this represents, as you go to the knee points, the error, okay? As you go to the linear, this is the error now 15% at this point, 23% here at this point, this 48%. As you go further, right, further away from the knee points. So how then we analyze? We want to see now, how do we check the not just the effect of steady state fault current, but also I want to find the DC effects. Where does DC effects came from? The DC components in the faults. Now, if we have, suppose I have a system where I have a bus and a feeder, okay, and I have a load. This is a load. And I have a breaker here, circuit breaker. And here I have a CT which measures, okay, which some here, let's say a CT here that feeds a relay. Okay, now I can model this. Now, when you try to, if there is a short circuit here, a short circuit somewhere, anywhere, okay, fault, I can model the circuit as a source, which is a source with now this breaker tries to open the circuit by the command from the relay, right? So I'll try to make a switch representing the breaker and the resistance of the impedance from the fault, from the source to the fault point, R, and the coil that represent the inductance that represent also from the source to the fault point, and this represents the short circuit, and that's the circuit breaker, the place we want to open, and this is where the CT is located. So I would like to see how the current looks like I during the short circuits. Okay. So now this is how we want to when you try to open, okay, or you want to close now circuits during short circuits. So I'm assuming now. Now this is a source, sinusoidal source, and let's try to see how the current looks like I okay, which has a steady state value and trend. Like this is from circuit number 2. Okay, so the current will looks like this. If you try to solve first order differential equation, okay, you will find it as I peak, the peak value of the RMS value. This is of the current, which is E E peak over the root of R square plus XL square under the root. So this is the impedance Z of the from the source to the fault point. Sine omega t plus alpha minus theta, and alpha represent here the phase angle of the voltage between the voltage and current. This is the theta, which represent the angle of the impedance Z, and alpha represent the instant at which you close or open the breaker. Okay, at what time? So the angle at which you have closed this breaker with respect to time. And this is e to the power minus t over tau represent the tau is the time constant, okay, of this, which is L over R. So tau is L over R. Okay. So as you can see, if you switch this at the instant where alpha is equal to the power factor angle or the impedance angle, you would end up with a sine of 0, 0. There will have no DC. This is the DC. This is the steady state AC component. This is the DC, decaying DC component and the current. So as a worst case scenario, so what I want to study, I want to stay with not at there is no DC. I want to study the worst case scenario. Worst case scenario when the DC is maximum, and this DC maximum when this angle difference is 90 degree, which makes sine here 1. So I'll assume now sine of 1 when we have theta minus alpha is pi over 2, which is 90. I have this is the worst case scenario. We call it the maximum DC offset condition. Maximum DC components. All right, now let's pass this through a CT. I'll see how the CT secondary looks like. Okay, now this is the current, primary current, IB, and this is the CT core, and this is the secondary current that will go to the burden, R burden. I'll see how the flux look like due to the sinusoidal AC current plus the DC primary current. Okay, so what is the voltage induced here? E at the secondary. Of course, I will also consider here I have a resistance of this primer of the secondary winding RS. So what will be this E secondary or V at the secondary? Okay, what I'll do, I'll just I primary. Okay, the voltage induced here E is proportional to N d phi by dt. Okay, and phi here the flux, N d or the flux linkage, which is d lambda by dt. Now, this is also equal the primary current IB divided by the CT ratio. CT ratio now the primary is 1 turn with this, and the secondary winding is n turns. Okay, so the ratio is 1 to n. So I'll say the primary current divided by the turns ratio n times, if you multiply now this current by RS plus RB, okay, which is this R total, I called it here. It gives you also E at the secondary. So let's call this ES. That's VS before. Okay. From this equation, I can find d phi by dt, which is IB over n squared times RT. And I would like to see how the flux looks like as a result of a current that has both sinusoidal component, which is the first component, plus a DC components, decaying DC components. Now, if I just go and integrate this part with respect to time, I have the current already. This is the current. It has both AC and DC. So if you integrate this, I will have two components for the flux. One is due to the sinusoidal AC current. This is the steady state fault current, and the second is due to a DC current. I will call it now the DC component of the flux. I will see how these two flux looks like. Now, in the previous lectures, we were sizing CT based on this AC sinusoidal components. We didn't consider this DC. Now, if I integrate for the AC, if I integrate the first part, I'll get this relationship. Okay, I don't want to go to proof. You can. And also if you integrate the second part, which is IBRT n square times E minus tau over tau, I will get this relationship. Okay. Now, if you add these two, it gives you the total flux as a function of time. Now, what is the maximum flux in AC? So AC is sinusoidal, right? The AC here is sinusoidal. AC flux, phi AC. And its maximum is this value, IB, right? This value. Of course, it's minus, means it is like minus sine wave. Okay, doesn't matter. So this is its maximum, which is this value. And for a decaying DC, the flux due to the DC current, its maximum when time at time 0, E minus 0, 1, so 1 minus 1, 0. Okay, so you have 0 time, 0 flux, and it's increasing with time. So the maximum value for at time infinity, this becomes 0, and you will reach maximum at steady state. So this is always, okay, maximum. The maximum value is this for the flux. Now, to size a CT, before we were sizing CT based on this magnitude of flux, and by assuming this flux for BH characteristics, this is the BH characteristics. Okay, the BH. I am assuming at the previous analysis that my knee bonds correspond to maximum flux of the AC. Okay. However, now we didn't consider in previously the addition of this to that. Okay. Now, if you add this, we will exceed this maximum knee point due to the DC flux in the core. Core will saturate as a result of this. Now, if we add these two, we'll take the worst case scenario, we'll add these two components, these two AC components, we'll get this. This is the negative sign, right, as I showed you before. And this is the DC component. This is the due to DC, phi DC. And this is phi AC. If you add them together, you get a sine over a DC. Okay. Now, before we size the CT based on this value, but as you can see, phi can go up to this value, and CT would saturate in this case if I didn't consider the DC effects, DC current effects on the core saturation. Now, How do we choose now CT such that it won't saturate? I have to choose my knee point such that it has to be the knee point of the curve, of the BH curve. This knee point should correspond to phi maximum, which has DC and AC. Okay, this is phi maximum, or if this is BH characteristic, the knee point has to be correspond to here, not to the maximum of the AC components only. Now to choose that, what factor I should take? I should take a factor that I see what's the ratio of phi DC maximum. This is the maximum at steady state with respect to phi AC maximum. Okay, so phi DC maximum, as I mentioned to you, is this value, and this is phi AC maximum. And if you take the ratio between these two, phi DC divided by phi AC, this cancel with this, RT with RT, N square with N square, you get omega tau from this relationship. Omega tau is L over R, right? Tau from here is L over R, the time constant of that circuit. And so omega L is XL over R. So tau is nothing but the XL over R. This is the time constant. And so so I can say that the phi maximum, which is phi DC plus phi AC, which is this phi maximum from here to here, give us, and phi AC, if I take it as a common factor, so phi AC is equal to phi DC is equal to phi AC times x over R. So I'll get 1 plus x over R times phi AC. Now, in order not for a CT to saturate, I have to choose my phi knee point such that at phi maximum is equal to the sinusoidal AC current, RM current, times this ratio, which is 1 plus XR. As a result, you know, what is X to R? And it depends on the system. For high voltage system, this ratio is, it could be, goes to a 10, okay? Depends on the also fault location. So what is the change now in the equation that we have to size CT is that for sinusoidal, the voltage that should develop at the secondary current, the CT should develop a voltage such that it's greater than or equal to IS steady state current times R secondary resistance plus R burden. But to avoid CT saturation, the CT should develop a voltage higher than IS times this value times the factor that we have derived here. And a fix of DC, okay, with the AC currents. So this is the change in our equation, okay? So I just add this 1 plus x over R in order to avoid the DC effects. Let's take an example in short. Suppose I have a switchgear. A switchgear is like a protection cubicles in which you have CTs, VTs, protective relays and breakers, and also you have it's a cubicle, okay? So I know how for that cubicle I want to have the choose if the CT ratio is if this class C200 is suitable for that switchgear or not. This CT is 600 to 5 ratio, and this is the CT class. The maximum short circuit current is, this is the steady state, okay? Short circuit current magnitude at steady state. This is at steady state. and RMS. So this doesn't include the DC effects, okay? It's only the sinusoidal component, which is only represent this, okay? The RMS value, which is this one. The XR ratio is 14. Which is XR, we said it is the impedance, the reactance from the source to the fault point. This is X, and R, this is the R resistance from the source to the fault point, including the source impedance. Okay. CT resistance is given to us, the CT resistance at the secondary side, connection lead resistance, and the relay resistance burden is given, and check if the CT is stable or not. Now, I will consider now I have no CT, I have no DC effects. Case 1, considering just symmetrical AC current. Okay, there is no DC. Now, if I take RS plus the total resistance, RS plus R burden, which is these two, I get 0.23. Now, if I take I secondary maximum due to fault, which is I fault divided by the CT ratio, so divided by 605, same as times 5 over 600, times the total burden plus the secondary resistance, I get 35 volts. So I just substituted in this equation, okay? So what will be the voltage that developed at the secondary of the CT due to that symmetrical fault current? It will be 35 volt. 35 volt, much less than the 200 voltage that this class the CT can develop and can withstand, so that the error will be within 10%. So 200 volt represents the limit that you should not exceed, okay, for the error to be within 10%. Now, let's consider the effects of DC. DC now, it's same as this, except I will multiply it by same as 35, which is here, we calculated, times the 1 plus X to R ratio. And that will becomes now, because this will be 15 times this, I'll get 528, which makes this C200 is not suitable in this situation if I want to consider the effects of DC current. All right, so from the steady state, this was suitable, but from a transient point of view, this is not suitable. Now, to make it suitable even from the steady state, from the transient point of view, due to DC, I have to choose CT, which is C800, right? Because we don't have C200, so we have C100, C200, C400. So this is a suitable class in order to avoid CT saturation due to DC current and the fault current. Okay, so now it sees that there is a much difference. نعم.
لو كان طلع عندنا ال VS 220 بيكون suitable or not?
It is well, it is close enough. This is a little bit higher than, no, which means you are a little bit higher than the 10% error. Yeah, يعني, which means if you exceed this, you will exceed the 10% error. Okay.
Okay. Okay, Doctor.
Okay. A little bit, so it's not too much different. Okay. But here is much different, right? Because you have almost double, is far beyond this. Okay. So what is the consequence? Here you will buy higher, more expensive CT as compared to C200. Yani the higher class means higher core size, higher, you know, yani it's not just C class difference, means, as I explained before, it means you have a core that is larger in order to develop a voltage which is larger, okay? Larger core means more expensive. Okay.
Okay.
All
Okay.
right. Now, can we يعني this class can handle even if the DC current يعني شنو this is the worst case scenario حتى لو ظل الفولت إلى ما لا نهاية يعني أنا اعتبرت T this T approach infinity لكن الفولت will not persist for infinity time. It will take some time يعني what I'm interested that the CT should not saturate during the relay operation time. يعني مجرد الريلي dictates that there is a fault and give a command to circuit breaker to open. I don't care if the CT saturated or not لأن الريلي has already taken an action okay to trap the circuit breakers. So I don't need to wait infinity يعني for sizing a CT proper CT. And this is called CT dimensioning. I want to choose now a CT that will not saturate up to a time T. Huh? Okay, I want to write up to time T here, somewhere here. Okay, during which I don't want CT to saturate. I don't care later if the CT saturate, if the relay has taken an action. So CT sizing based on CT saturation free. When I say CT saturation free means I consider this factor 1 plus X over R. This is saturation free. CT will never saturate. Okay. It will lead very expensive choice of CT and also impact the CT size, very large CT size. CT saturation does not occur instantaneously. It takes time until, so we call this time to saturation. CT shouldn't be saturated before relay takes action. This is what we are interested in. So most let's take now a time t such that we don't want relay to saturate. Let's say a relay should not saturate within, let's say, 0.1 second, right? I do a relay normally, let's say, detects a fault and takes an action, let's say, within 100 milliseconds, which is 0.1 second. So during 0.1 second, I don't want the CT to saturate. So this is my time to saturation. As a result, the equation I should consider should consider this equation, the summation of these two, right, into consideration, and with the factor of t. As a result, this is one factor only, but we have also another factors. So the voltage class that I should choose should be greater than. I will just rewrite this. KSS is nothing but is I. I. It is I fault. This is the short circuit current ratio, which is I fault divided by I rated secondary current nominal. Okay, so this is also I nominal. Okay, so this will go with this. Okay, so I can rewrite this as this is greater or equal than K transient factor. I'll tell you what's this times K remnant times the I fault, okay, maximum, which is I secondary now, okay, times RS plus R virgin. Of course, this is I fault referred to secondary of the CT, which is I secondary maximum. Okay, so this is I secondary okay, maximum during faults, which is the steady state fault current component. Okay, so the same as this equation. Same as this equation. Where is that equations? Yeah, same as this equation, except here we call this factor in general. At steady state, we call this factor is K transient factor. So this is IS and this is RS plus R burden. So same as this equation. Okay, so this is RS plus RB times IS secondary. Okay, times K transient factor, which takes into account the DC effect, okay, of the current, DC component. So in general, K transient factor is with this equation. That this is phi DC plus phi AC, okay? And this K remnants, it takes into account. So I don't have to have this because I have already substituted here. This shows you the maximum fault current with respect to the rated current of the CT. Remnant flux is 1 over 1 minus phi r, and phi r over phi s is the, if I draw the BH characteristics, or this is flux versus, so this is our phi saturation at the new point, for example, and this value is the remnant flux, phi remnant. Even if you remove the current, there will be some residual flux in the core. But ideally, before we assume I have no residual flux, before I assume my characteristic passing through 0. Yeah. This is ideal. It's non-ideal. I'm assuming now I have residual flux in the core. Now, the ratio between phi r to phi s, okay, suppose I have 10%, so this will become 0.1, and this is 1 minus 0.1, 1 over 0.9. This will give you a factor greater than 1. This factor, when phi r 0, right, when phi r 0, which is the ideal case, means K remnants equal to 1. Equal to 1, right? So this is always greater or equal to 1 factor. So equal to 1 when you have no, if I consider there is no effects of remnant flux, or an ideal case. So this takes into account the remnant flux effect, and this takes into account the DC current and the fault current. So generally, assignments will consider how do this effects of this, okay? Effects of TS. What is TS here? TB, you know TB, which is the primary time constant, which is the same as I showed you here, which is L over L of the primary side circuit over the resistance. But TS represent the secondary time constant, which is the magnetizing current, magnetizing branch of the CT inductance over the total burden plus the secondary resistance, which is RS plus. This is the secondary side of the CT. Okay, so these are normally we should know these. And sometimes for standard they are estimated for high voltage. You have this is these values for TB and TS. Now the second assignment, analyze these equations. Okay, see how the effects of TB TS on CT sizing. So as one approximation to this equation, we'll assume a worst case when this becomes maximum, when this becomes +1. Okay, So this becomes maximum because sine becomes plus or minus, right? 1. So when it becomes sine is minus 1 times minus, this becomes a plus. So this makes the worst case scenario for K transient. This is the first approximation. Second approximation will consider T is normally in real life, T is much larger than TB. Then we'll get a second approximation that I have no TS, no sine, right? Then we'll end up as at T approach infinity, you'll find this equation becomes, so at T approach infinity, you will see the K, you can prove it this, you can K transient factor will becomes x over 1 plus x over r. Okay, which is 1 plus omega, okay, TB. 1 plus omega L over R. L over R is the primary. So this becomes this, or if you approximate this at T approach infinity, you'll see it is so, which is the same as the previous factor we derived at the studies at, as T approach infinity. Here as T approach infinity. So the K transient factor is nothing but it's to provide the effects of decaying DC current on the CT saturation. How's the CT affects? So we can repeat the previous problem here. If I don't want the CT saturate at time up to 0.1 second, so the difference here, I'll just this one, this factor will be replaced by K transient factor. Okay, K transient factor, and you have to calculate it using this equation. Okay, in general, or we can use the approximate equations as you will see in the inshallah assignment 2. Okay, this is factor. You have to know also the remnant flux factor. You have also to multiply this also by K remnant. Okay, so K remnant times K transient times this, it gives you the class that you should choose. Okay. Now, how's that affects? Why we are worried about the CT saturation due to a DC or due to remnant flux? Now, suppose we have no saturation. Without CT saturation, now these are two curves. One of them represents the primary current, the other represents the flux. For no saturation, both the flux and the currents are sinusoidal. Okay, and as a result, if you see the secondary current also looks like a sinusoidal. This is the secondary current, which is the lower value, and the primary current. And the difference between them represent, now this is the primary current referred to secondary as an ideal, and this is the secondary. The difference between them represent the error, okay? Now with saturation, the flux, now this is the current, okay, which has, this is a sinusoidal current. It's symmetric around 0. Right? While here it's not symmetric, it has a decaying DC in it. So it's like it decreases with time. Okay. So it has a DC with the AC component in it. As you can see here, the second curve represents the second curve. This represents the flux. Now flux gets to its maximum, it gets clipped. Okay. When it reaches to maximum, it clips saturation. Clipped flux. So because of this, the current also will be, its shape will becomes distorted like this. This is the secondary current. Instead of sinusoidal. Okay, so that's due to saturation as a result of a DC. Okay, for example. Now, if you have a situation where you have no remnant flux in the core, this is the secondary current, right? This is the ideal, the input current, and this is the secondary current. Initially, there's no difference, but then it developed at the second cycle, developed CT saturation, but this is not due to remnants, due to the DC. Now, when you have a remnant flux of 50%, and this is the ratio of phi residual over phi saturation is 50%. I'll get saturation even from the beginning. Okay, this is the current. So even it becomes worse than the situation we do have now. Now imagine I have a relay that has this current passing in it, and what would happen? Okay. So first of all, now we know before I see the effects of the saturation in the relay, that the factors that I can see the saturation are secondary burden, the primary maximum current, the DC offset, and the remnant flux in the core. And how that affects CT saturation affects the relaying. It reduces the. Now, how do you reduce the effect of CT saturation? By reducing the magnitude of the secondary current by choosing a higher maybe ratio. Now, what's the effects of DC? Sorry, here. What's the effects of CT saturation on the protection side? Because of this, as you can see, the magnitude of the current will get reduced. If you take the fundamental of the this distorted secondary current, you'll see its magnitude is reduced as compared to non-saturated current. So first of all, the magnitude of current will reduced, and the angle error, also the phase error between the secondary current will increase. The angle error. It's not just the magnitude has dropped. Also, if you track the phase relationship between the distorted current and the non-distorted current will be, there is a phase shift. So there is an angle error also. As a result of these two errors, you will have some relays, such as overcurrent relay, will have longer time, or sometimes it might not operate if you have fully saturated, because overcurrent relay operate based on principle of magnitude of current. If the current, if the fault current is higher than at setting, relay operate. Now, this current, because of the saturation, has dropped below the settings, so the relay will not operate. Or even if it is higher than the setting, but the relay overcurrent relay operate based on this principles of time versus current. It is inversely proportional. So if the current has dropped from this value to this value because of CT saturation, it will take longer time to operate. Okay. So it will affect the relay operation. Okay, in this case. And also it will lead to differential relay to maloperate. Differential, inshallah, there is one chapter on differential relay. It's only take a difference between two CTs. If one CT is saturated, the other not saturated, there will be a false difference of current between the two. Is not because there is a fault, because the one of CT is saturated with other is not saturated, and the difference due to that, and the relay, differential relay, will maloperate. Distance relays also might underreach. Okay, and distance relay takes the voltage over the current. Now, if the current has a drop because of CT saturation, this relay's impedance will measure impedance higher than what is actual, and as a result it will underreach. So that's also affects. If you have directional relays, which take the difference between a voltage and current angles into account, because angle also has get distorted or changed, that might affect also directional relays. So we have to make sure that the CT should not saturate, okay, by choosing a proper CT class. All right, with this I'll try to close this chapter, this part of the second part. I would like to quick within 15 to 20 minutes. I'll try to finish this as I promised. Do you have any questions so far regarding the first part, transient?
No, doctor.
Oh. This is just a graph that shows you. I got it from your textbook. Okay, that this is the same. This is the flux shape. Okay, if you, now flux, it has this shape. Okay, now this is the flux linkage. Now let's assume this is the saturation level. Okay, now if the flux exceeds the saturation level, the CT will saturate. Okay, so I1 now represent the primary current. Okay, the current without saturation. Okay, now if you refer to the secondary side, now this current with the DC, as you can see, it's not symmetrical. Now, and I2 represent now your secondary current. Now, as you can see from this, if the current now, if the CT not saturating, yani the flux is still within before the green line, the sinusoidal, the current at the secondary is sinusoidal, okay? But once reach this point, okay, this point, it will saturate, so it will be like this, it goes to zero. Now until the saturation here, now from here to here, CT saturation area, because the flux is higher than the city. Now, when it comes back to its normal, back to the normal value, then the currents also returns back to its regular values. So here also, as you can see, the current, the flux at this point exceeded, so CT also will, okay, so we have a signal like this. This is the current. This is the shape of the current. Now, at this point, right, the CT will also saturate, so it will come like this, and so forth. So this is the shape of the secondary current due to CT saturation. So what we want to do, we want to make now our choice of the class, this line green as high DC, okay, higher than the maximum value that you would experience, okay. All right, for the voltage part, it is a quick, inshallah. I'll try to take 10 minutes to 50, maximum 20 minutes, inshallah, right? So what in this chapter, in this section, VT, what's the VT connections? This is not in your slide. I added this. The types of VTs, voltage transformers, the equivalent circuit voltage transformer, impact of transient on current voltage transfer. I'll show you what's or capacitive voltage transformers, and I'll give you one example. Now, by this time, you know this is a CT and this is the VT. Okay. For VTs normally, you know, the output of the voltage transformer is standardized at 115 and 120 volt, depends on the standard. For the connection of the voltage transformer, as you can see, this is one VT of one phase. This is second, this is third phase. So at the secondary side, we can connect them now as this is now this is the primary winding. The secondary side is down, so we can connect them either star or like this configuration. This is a star. We can connect them as delta connection, delta in this case, or we can connect them as open delta. All right, as an open delta, like this one, or they call it V-type. Now we'll take here like phase B as a common, and phase A to this coil, phase C. This is not the right. I will just correct this one. This has to go here. Okay. So from this phase goes to phase C, or this could be A, okay? And this is phase B, and this goes to phase A. And for the secondary side, also now phase B becomes common here, and phase C is here, and this is phase A. And this is the phase becomes a reference. Now we have two voltages. This voltage represent, okay, VCB, and this voltage represent VAB. This is called the V-type or open delta connection. We have another connection for VTs, which is a broken delta. Okay, a broken delta. Now this is same as this is A phase, B phase, at the primary side of the VT, and this is the star point, and this is it's like a delta into beginning, but we open this terminal. Okay, so this is called open delta, or sorry, broken delta connection. And the broken delta connection is got to get the zero sequence voltage of the three phase. Do you have a zero sequence voltage or not? And because this the voltage, these voltages is the VA plus VB plus VC, right? So this is the A voltage at the secondary side. This is V voltage, and this is VC voltage. If you add them, you get the three V0, which is the zero sequence voltage. Okay, so these are in terms of connection. We have some transformer which are primary star. We have three winding transformers. This is a star and broken delta, which is shown like as broken delta, like this. So you have primary one side, but secondary have two star connected, the other is broken delta, so I can have two output. In terms of construction, we have two types, electromagnetic type, and we have the capacitor coupling voltage transformer, or simply we call it capacitor voltage transformer, CVTs. We know that the electromagnetic type, this is the same as what you have covered in machines. Normally, VTs here are designed to operate at normal rated voltage, which is from 0 to 110 of the rated voltage. Now, normally during fault, the voltage drops down, so we don't have like an CT where the current goes very high. Okay. However, might be some situation where have over voltages, okay, situations due to switching and so forth. However, these types of VTs becomes very expensive when you go to extremely high voltage, like greater than 345 kV. And as a result, we use capacitors as a voltage dividers, okay, before we connect this conventional voltage transformers. So the output voltage standardized at 115 volt line to line to, as I mentioned, to 120 in USA. This is the equivalent circuit. I don't want to go over that. So what's the error here? Error is between the voltage at the secondary, okay, that you will receive with respect to the ideal voltage at the secondary, okay? So if you have an ideal transformer, this secondary voltage is determined by the ratio. But then because of this drop in the series and leakage impedance of the primary and secondary, you will have a voltage here different than ideal. And this error, okay, this is the ratio times the secondary voltage, give you the primary voltage minus the actual voltage. Over this gives me the error. Or I can also take the V secondary and compare it with this ideal secondary voltage. The difference and divided by, let's say, ideal voltage at the secondary. It gives me also error. Also, I have phase error. This is not just ratio error, also the phase angle error between the primary here expected to be in phase with the secondary. So if there is a phase difference, we call it between the primary and secondary, we call this a phase error. Now standards, this error is not too much, you know, doesn't worry us from the protection point of view as compared to CTs. Okay. Also the burdens of BTs are standardized. Okay, and these are according to ANSI. The VTs has a standard burden of 12.5 volt ampere up to 400 volt ampere. These are the burden, standard burden identification. Instead of, we say, B1 or 1 ohm burden in CTs, no? And B2 for 2 ohm burden, B4 and B8. I'll just consider here the construction of CVT, which is because the regular transformer you already know. Now, for CVTs, capacitor voltage transformer, its construction like this. And this column, this is the porcelain shell from outside, porcelain insulators. Inside this porcelain, this is the terminal of where you connect the cable, okay? So this is the terminal, which is now this point. Okay, inside here I have a bank for capacitor VT, we have a bank of capacitors, okay, here. Here we have a bank of inside capacitor banks. Okay, and these capacitor banks, okay, we have a tab somewhere here, which connects now. We connect this to a transformer. we tell like a voltage. I don't want this voltage. I want a voltage. This now represent, let's say, C1. This from the top point tab to the middle tab or to the this point, and this represents, let's say, C2. So this represents a voltage divider. This is filled with oil or with gas. It depends on the cooling media we use, and then it's connected to first to a reactor, which is number series reactor, which is this one. Okay, so it's like I'll take this point as in series with a coil down. Okay, and then we'll connect this, okay, with this to a transformer. Okay, the regular transformer, and then I'll take the output from here. So this transformer is the this backside. This is the transformer. So this is what this series capacitors, okay, normally reduce. So these are the equivalent circuits of this. Okay, so we have capacitors, a bank of capacitors here. So we'll the top ones to the tab is C1, the others is C2, and this is the compensation reactor, and we have this is the regular transformer, and then we have some protection, sometimes ferro-resonance suppression circuit, which I will not cover in this course, the effects of this. This is just a filter, okay, filter. And then we connect here the relays and, okay. So instead of connecting this directly to this transformer, okay, voltage V, this is the VT. We first take the voltage and drop it to a certain value, then we take it, step it down by using this transformers, okay. So what is the purpose of C1? C2 is just as a voltage divider, it acts as a voltage divider, okay? And this compensation reactor, its purpose to make sure that this voltage and this voltage, okay, are in phase, and to compensate the effects of the capacitors. So I would like to make this voltage and this voltage in phase regardless of the burden, okay? Suppose this is the relay burden, this is R burden, okay. So I want to make these two, the V here and V here, are in phase regardless of the current due to the burden, okay. And this is just a row normal, which will reduce this to the required voltage which I wanted, which is 115 line to line, or 115. This is what I want, 115 to 120 volt over, of course, √3, okay, for phase voltage. Because this is now, this represents one phase, okay. So this is that I explained to you, the purpose of the coupling capacitor, purpose of the compensation reactor, purpose of the step down transformer, which is this one, and the purpose of the ferro resonance. Ferro resonance is just to protect the relays against over voltage. If you have switching surge, and this is voltage because you have capacitor, this goes high. So to protect this relay, we have a filter here which would will make this impedance low during high voltage, and will try to short this, okay, to protect this due to high voltage. So it's like a filter, high pass filter, okay. so, like a bandpass filter, sorry. For a certain frequency, it will pass it and ground it. So it's like to avoid, this will avoid dangerous and destructive over voltages caused by the ferroresonance. When you say ferroresonance, ferro is the ferromagnetic materials, which is the core. When the iron core, okay, which is the magnetization of the core, okay, get resonated with the capacitors that we have added. So we have like a now filter, resonance filter. This this will create a resonance at resonance frequency. The voltage can go very high and destruct the relays. So this is another protections which I would not cover in, so far in this course. So what will focus here? How do you choose the value of this? Okay, how do you choose now the value of this? So to design the CVT. Okay, so this is the equivalent circuit. This is the voltage from the bus to the ground point. This is per phase, V bus. C1, C2 are the acts as a voltage dividers, capacitors. And the voltage here is called this V Thevenin. And this is the compensation inductor. And this is the voltage at the primary side of the voltage transformer, step-down voltage transformer. And this is the voltage at the secondary that will go to the relay. Okay. Now I can take the Thevenin equivalent circuit of this part as what is the Z Thevenin here? If you ground this one, remove the source, right? This becomes parallel with this, so the C Thevenin becomes C1 plus C2, right? And now what's the voltage here? Voltage like V Thevenin is V bus times ZC C2 over ZC1 plus it's like voltage divider rule, right? And if you must substitute ZC2 1 over J omega C2 and ZC1 1 over J, I will get this as a voltage divider. So this is the voltage at the bus, which is this voltage, and this is the voltage at the Thevenin, which is so that's same circuit, but I replaced this with this equivalent circuit, the Thevenin equivalent circuit. Now, the current, what will be the voltage here? The voltage here will be this V Thevenin minus the drop here, right? Which is V Thevenin minus I, the current here I, times this impedance, which is J omega L plus the Thevenin equivalent circuit with a Thevenin capacitance or impedance 1 over J omega C Thevenin is this C1 plus C2. Now, as you can see, to make this same as the V Thevenin, and they are in phase, to make them also in phase, we have to make the C Thevenin cancel with L. So I have to choose L such that cancel this. So if I choose this equal to this, okay, so this is like minus J, right? 1 over J is minus J. If I choose omega L is equal to 1 over omega C1 plus C2, this two cancelled at 50 Hertz, okay, and VB becomes V Thevenin always, regardless of the burden I, because burden as it's changed, it will change I secondary, right, which will change I primary. Okay. So in this case, there will be no change because I already cancelled the drop here. So choosing now L, so I want to make this times this should equal to this times this, and from which XL, XC Thevenin should equal to XL, and from which I get the that L has to be equal to 1 over omega square this. So this is how I choose the I design the compensation inductor or reactor. And as a result of this, at 50 hertz, of course, what is omega here? 2 pi f. And what is the value of S is the 50 hertz if you are in Bahrain and 60 hertz for Saudi Arabia. Now, at that condition, VB becomes V thevenin, which is equal to V bus times C1. So we make sure that this becomes in phase with this, regardless of the burden. And as a result, this voltage also becomes in phase with this, but at a reduced magnitude. Let's take an example. This is example I will close. A CT is required to be designed for 400 kV line using a voltage transformer rate. This is the step-down transformer, which is this one. Okay, so the voltage here is 132 kV, 210. Here 132 kV over √3, and here 110 over √3. And this is the rated power of that transformer. Okay, and I want to find the coupling capacitor C1 and C2, the value of the compensation reactor L, and the burden in ohm that can be connected across the secondary side, which is R burden. This is what is this value maximum. So V thevenin, as I say, we V thevenin at the end when we connect the capacitor. We choose this such that this cancels, so VB will become same as V thevenin, and V thevenin equal to C1 times VB bus ala C1 plus C2. So this is direct, and V bus we have it. We know V bus, but and V thevenin same as VB, which is 132 kV. Substituting this value and this value, we'll get that C1 over C2 equal V thevenin on V bus, which is 0.33, and from which we know from this relationship that C1 has to equal to 0.33 times C1 plus C2, from which we know C1 should equal to about 0.5 of C2. And now I have so many choices here. For a given value of C1, so microfarad, this has to be 0.5 microfarad. This is 1 farad, this has to be 0.5 farad. So that has so many choices. So from the design point of view, should be higher value is better than smaller value. For all cases, I'll get the same voltage division achieved. So we'll study this on the effects of the transient for choosing higher values of C's or lower values of C's. Now, for this case, let's assume the value of C2 is 50 microfarad. Then C1 will be half of that, 25 almost microfarad. Now, once I know C1 and C2, I can find now the compensation inductor value by substituting in the equation directly. Now here I assume 2 pi f. This is the pi, and the frequency is 50 to by 50, 100. And I got the inductance. And the burden, because I know this is the maximum power of the transformer, so this is your maximum burden that should not exceed, okay? So and the voltage is known to be 110. So for we know that V square over S gives you the impedance. So V square line to line over S give you the burden, which is 12.1. So this is the burden should not exceed this. Okay, this is how the ferroresonance looks like, which is I don't want to describe, but here I will see how the effects of the transient effects of the capacitor voltage transformer. So here the capacitance values has an effect. The moment at which fault occurs, okay, has an effect. The ferroresonance suppression circuit has an effect. The burden, whether it's resistive or inductive, has an effect on the CT transient. I'll show you now the values of the capacitors. Now for large C, okay, capacitor, the blue line represent when you have very large capacitors value used, and the blue line represent lower values of capacitors, okay, C1 and C2. Now, as higher capacitor, it will give you a lower transients, because now what happens here, a fault occurs at here. Ideally, the fault occurs very close to the voltage transformer. A fault occurs here. So if the voltage here occurs, and this is solid to ground, the voltage here is zero, supposed to drop to zero. Because of the capacitors, okay, this is the moment at which fault occurs, the voltage is supposed to be like this, ideally. And because of the capacitors voltage division, we have a DC fix before it gets to, it has a transient before it goes to zero. And as you can see, if you have very large, extremely large capacitors, you have, very large capacitors, you have lower effects because this leads to, as compared to lower value of capacitors. But going for very large capacitors means more expensive. This curve represents the CVT transient at different time of the faults. So this happens when the faults, when the voltage cross zero. Okay, fault occurs when at zero voltage instant, and this fault happens when the voltage is maximum. Fault occurs at this point. And as you can see, this is the ideal case where the voltage should be looks like this at the secondary if you have no capacitor voltage division. Okay, and the second one represents when you have C capacitor dividers. As you can see, the transient is worse as compared to the ideal case. And now, if you have faults at the peak, you have this is the ideal case where the voltage should look like, and this is the transient. And you have here, as you see, the moment, but this is not in our hand, right? I cannot guarantee fault will occur when the voltage becomes maximum or when it is cross zero or somewhere else. But however, we should do these studies to see what's the worst case scenario for the transient voltage and how this affects the relays operations. For distance relays, inshallah, I have one chapter on this. A distance relay operates when the impedance seen by the relay falls inside this circle. If you have now the fault now is outside the circle, is here the fault. So if you have no CVTs, the impedance trajectory will come to the fault points. It doesn't go inside the trip area of the relay. And however, if we have CVT transients, the trajectory of the impedance will comes inside the trip area and then will go to here. So because it goes inside, the relay will think that the fault is inside the protected line and it will trip the circuit breaker. So that's it will lead, so CVT transient could lead to a maloperations, and we have to take either in relay design, okay, where the relay knows this is a CVT transient, okay. With this, I would like to close this chapter, okay? And if you have any questions, you can always ask me at the beginning of the next class, okay? Is there any questions? Okay, yes, is there any questions?
No, doctor. Okay.
Okay, all the best.